So we've talked about examples of gases and doing calculations with pressure and volume, temperature and moles of single gases. But what if we have mixtures of gases? What if we have a tank with 2 or 3 or even 4 gases in it? How does that affect our calculations and problem-solving abilities for pressure and volume and temperature and moles? Well, the main concept that allows us to solve these problems is called Dalton's law of partial pressures. So Dalton's law of partial pressures. Okay. What Dalton's law of partial pressures allows us to relate is how the pressure of one gas in a mixture affects the total pressure of the gas in a mixture. So first thing, we probably need to know what this word partial pressure means. So let's break it down. Part. The partial pressure is the pressure exerted by one gas in a mixture. And it is part of the total pressure. So if we have 3 or 4 different gases, there's going to be 3 or 4 different partial pressures. So for example, let's say we have this tank over here of gas A in it. And we notice it has a pressure of 300 millimeters of mercury. Okay? Oops. And we have gas B over here with a partial pressure of 400 millimeters of mercury. And you want to know, if we combine these two gases together, what is the new pressure going to be? Well, Dalton's law of partial pressures is relatively simple. It tells us that the total pressure of a gas is equal to the sum of the partial pressures. So partial pressure of A plus partial pressure of gas B plus partial pressure of gas C, on and on for however many gases there are. You add them all up, you get the total pressure. So this is one way to express Dalton's law of partial pressures. Therefore, in this case, the total pressure, PT, would be equal to the sum of the partial pressures. So PA plus PB, which would be 300 plus 400, which, as you can tell, because before I erased it, was 700 mmHg. So one way of looking at Dalton's law of partial pressures. You could also be given the total and asked to solve for the partial of one or the other. Either way, this is one way to express Dalton's law. Another way is a new representation that's different than what we've seen in regular chemistry. Another way of talking about the partial pressure of a single gas. So let's say, again, we have like some tank. It has 3 gases in it. Gas A, B, and C. We know that there's going to be some total pressure here that's going to be equal to the sum of the partial pressures. But is there a relationship between these two things, the partial pressure of A and the partial pressure of the total pressure of the mixture? Yes, there is. And the representation for that is the partial pressure of gas A is equal to the total pressure of the gas times the mole ratio of that gas. So XA, chi, the letter in the Greek alphabet chi, this is the partial pressure, the mole ratio, where the mole ratio is represented by the moles of A over the total moles. So just think about this conceptually. What this tells us is the total pressure of a gas times basically some percentage, some fraction of the total moles is going to give us the pressure of that certain gas. Same thing for B, the partial pressure of gas B would be equal to the total pressure of B times the mole ratio of gas B, where XB is the moles of B over the total moles. So what we can see clearly is as this number of moles increases, this value of the mole ratio increases, so therefore the partial pressure of that gas is going to increase. So there's clearly a direct relationship between the number of moles of a gas and the partial pressure of that gas in a mixture. So these are the 2 separate ways to represent Dalton's law of partial pressures. You need to know this one as well as the one on the front. Now let's apply it to a few example problems. So, for example, a scuba tank is filled with 3 gases. The partial pressure of O2 in the tank is 0.0 That's cut off, but it says 87 ATM of N2 is 1.1 ATM and CO2 is 0.01 ATM. What is the total pressure of the tank? Well, what I strongly recommend, problem-solving strategy, draw a picture. Always draw pictures. Always draw pictures to represent, turn words into pictures. Model. So we have a scuba tank, okay? I got my tank here. It has 3 gases in it. It's got some O2. It has some N2. And it has some CO2. Okay? So what's going on? I'm trying to figure out the total pressure. Well, what do I know about total pressure? That's my goal. I know that it's equal to the sum of the partial pressures. Partial pressure of A plus B plus C, on and on. Well, in this case, I only have 3 gases. So it's just going to be the total pressure is equal to partial pressure of those 3 gases. So O2 plus N2 plus CO2. I would just plug in my numbers. 0.87 plus 1.1 plus 0.10. Add those all up. I would get a final answer of 1.98, but with sig figs, 2.0 ATM. Relatively straightforward. But I do want you to drill home the idea of drawing a picture and setting a goal, backwards problem solving for that problem. Let's step it up in difficulty. A sample of air is designed that maximizes plant productivity. This sample of air contains 1.5% CO2, 18% O2, and 80.5% AR. If the total pressure of this sample of air is 745 millimeters of mercury, what is the partial pressure of each gas? Okay, again, I'm going to draw a picture real quick. Okay, so I have about 1.5% CO2. That's not very much. I have 18% O2. That's a little more. And then the rest is AR. I want to know the partial pressure of each one of these. It's not given, but I am given the total pressure is equal to 745. Well, let's think. What do I know about partial pressure? Well, I know the partial pressure of one gas, like so for CO2, is equal to the total pressure of the mixture times the mole ratio of CO2. Well, let's think about what's the mole ratio of CO2. That is how many moles of CO2, I should say CO2, over the total moles I have. Well, I'm not given any moles, but I am given percentages. I'm given 1.5%. So essentially, this mole ratio is 1.5%. It's telling me that 1.5% of all of the mixture is CO2. Another way of saying that is 1.5 moles out of 100 moles. Think back to when we did empirical formulas. We assumed we had 100 grams. In this case, assume you have 100 moles. So if it's 1.5%, that means 1.5 moles of CO2 out of every 100 moles belong to CO2. So if I wanted to figure out the partial pressure of CO2, it'd be the total pressure, 745, times 1.5%. So what is that as a decimal? 1.5 out of 100? Well, you'd plug it in to right here. You do the math, and we'd get 11.175 millimeters of mercury. You can check for your sig figs. What about my O2? Well, P of O2 is going to be equal to the total pressure times the mole ratio of O2, which in this case is 18%. So it'd be 745 times 18 over 100, which is going to give me a final answer of 134.1 mmHg. And last but not least, my argon, which is 80.5%, P of AR, is going to be PT times the mole ratio of AR, which is going to be 745 times 80.5 over 100, which is going to give me a final answer of 599.725. mmHg. I'm not too worried about sig figs right now. You should be. But I want to think about how could I check if my answer is right. Well, I know that the total pressure is always equal to the sum of the partials. So if I add up 11.75, 134.1, and 599, I better get this number. Third problem. Let's look at it a slightly different way. Consider the diagram below. Okay, well here's your diagram. Okay, in your diagram we have some different molecules floating around. Okay, where the orange actually doesn't matter what each one is for this case. Let's go ahead and tackle the problems. So part A says, which gas has the greatest partial pressure? Explain. So there's three options. We got blue, black, and orange. Well, we know that partial pressure and number of moles are directly related. So basically, the greatest partial pressure is going to have the greatest number of moles. So therefore, the obvious answer, if we look at the number of moles, we have 4 of the black ones. So this one, because we have the most moles. Part B can be answered in a similar way. Which gas has the lowest partial pressure? That's going to be one with the fewest number of moles. So that's going to be our orange one because it has the fewest moles. But now let's go ahead and tackle part C. If the total pressure is 3.8, what is the partial pressure of each gas? Okay, so I'm thinking backwards. Goal, partial pressure. What do I know about partial pressure? Well, I know that partial pressure of, for example, the orange is going to be equal to the total pressure times the mole ratio of the orange. So in this case, that's going to be the total pressure of 3.8 times the mole ratio. Remember, mole ratio, this is the moles of orange over the total number of moles. Well, how many moles of orange do I have? I have 2. How many total moles are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom. Plug it in, solve it. I would get 0.84 ATM. Let's go ahead and do the next ones. Okay? Partial pressure of the black molecules would be the total pressure 3.8 times the mole ratio of the black one. Well, I know I still have the same total 9. I have 4 moles of the black one, so if I multiply these out, I'm going to get 1.7. And for the last one, blue, partial pressure of the blue gas, that's going to be the total, 3.8, times the mole ratio of the blue. Well, there's 3 moles of blue for every 9 moles of gas. I do the math here, I get 0.84 ATM. Think, how could you check yourself? Do they all add up to what you would expect? Yes, they do add up to 3.8. Also, just think about which number should be the biggest. Well, we said is the black one because it has the greatest number of moles. Which one has the greatest volume? Or excuse me, pressure, 1.7 is correct. And I want to apologize, there's a slight error here. This should be 1.3. 1.3 ATM.